This is notes from AV Tankhiwale. Now, our subject is Nobel laureates 1928, 78, 79, and this is the Institute of Science, and this Shrikant is given to Ashwini Prasanna, his granddaughter, who Shrikant interestingly has said that in Q hope she jumps this one too. So they had a Q, he thinks that Ashwini jumped Q in marrying much before everybody, all her siblings, and she jumped the queue in getting us the first grandchild. So Shrikant hopes that she'll jump the queue in getting a Nobel Prize also. Now, from the notes, excerpts for Contemporary Frontiers in Physics, Victor F. Wiskoff in Science, 19 January 79. Table 1 is Unifying Principles of Physics, Principle author theory, and 1 is Unity of Natural Laws wherever and Earth, Newton. 2 is Unity of Heat and Mechanics, Mayer, Hell, Custer, Joule. 3 is Unity of Electricity, Magnetism, Faraday, Maxwell, Option. 4 is Unity of Space, Time, Motion and Gravity by Einstein. 5th is Unity of Physics, Chemistry and Materials by Quantum Mechanics, and Unity of Atom, Nuclear and Subnuclear Field Theory and Phenomena. Table 2 is the Quantum Ladder. Subject is chemistry, optics, materials, body, complexity, so easy range EV is up to 1000, and location is Earth, space of other stars, Earth and planets of other stars, each planet of other stars. And 2 is radioactivity, fusion, mission, nuclear reactors, 10⁵ to EV range is 10⁵ to 10⁵, and location is interior of stars. 3 is antimatter, mesons, heavy electrons, short-lived entities and quantas. So their EV range is 10⁵ and to higher. And these are neutron stars and big bangs and unknowns. So that's the quantum ladder. So in that first was the chemistry, optics, materials, etc. up to 1000 EV. Yeah, so this is on Earth and planets of other stars. The second was radioactivity, fusion, fission, in which you produce EV of electron volts of 10⁵ to 10⁵. And that is for interior of the stars. And third is the antimatter and mesons, heavy electrons, short-lived entities and quarks. Quantum mechanics is a unifying principle, but it has brought about a division of physics into different the realms of phenomena. This is because there exists a threshold of excitation for dynamic systems. From any dynamic system, the threshold becomes higher as the dimensions of the system decrease. The ordinary principles may be referenced as quantum ladder and the order principle. In atomic and molecular realm, the energies are low so that atomic nuclei remain unexcited, etc. The recent discoveries, last decades, have been unusually fruitful due to the growth of new instruments, that is, lasers, plasma, synchrotron radiation, rockets, computers, colliding beam devices, synchrotrons radiations, which ponders intensities of 10 to 6. And superconductors, super fidelity, helium-3 accelerators impact to particles of order of tetrapetal volts, that is 10 to 12, or technology of collecting, etc. Protons beams have been developed. And nonlinear physics, where nonlinear elasticity occurs, relations occur, mathematical understanding becomes difficult if they are small. One can use perpetual particulate fields limits. Nonlinear are important in particle physics because string interactions which are not amenable to approximation vehicles. Amongst the new forms of behavior introduced by nonlinear are the so-called solutions. Local charge disturbances of a few that behave and that we have not unlike particles. They may even turn out to be what we observe as elementary particles. Now, particle physics, it's L. Particle 1978. So, fermions, they have quarks and leptons. Name is U, charge is 2/3, leptons is E, and name is E, and charge is 1. Quantum D is 1/3, minus 1/3. L. Particles 1970. Particles of particle physics. UDSCB. So they have a charge of 2/3, minus 1/3, minus 1/3, 2/3, and 9. Leptons name change E, nu, E, and gamma, nu, neta, and T. 10101. Type of interaction is strong electromagnetic, weak, and gravity. Source of interactions are quantum color. Carriers are glucon, photon, electric charge. All particles interminable mesons, gravity, easy, and gravitation. A decade ago, the news was that quantum force constitutes a bargain. The baryons and mesons hadron was considered a vague hypothesis. Mm, had behave as if they are made of quantas. Now there is no doubt that the nucleons, their excited state, are composed of three quarks, and the mesons are composed of quarks and antiquark pairs. A funny point was reached when, with the results of S. Friedman, H. Kendall, and R. Taylor, who observed deep inelasticity satisfying of first elements with nucleons at SRAC. The observation had all the characteristics of electrons being scattered by charged subnuclear particles much smaller than protons. It was the release of Rutherford experiment of submatter of physics since it revealed the existence of small concentrated charges within a nucleon. The quarks were indeed seen just as Rutherford saw the atomic nucleus. Similar deep inelastic scattering should we make with the beams of neutrinos which were scattered by quarks with weak interactions. These experiments confirmed and extended the findings of electron scattering experiment and provided additional support for the quark hypothesis. Quarks were found to be particles with spin of half. They carry fractional charge such as +2 by third or -half. They are point-like and not very strongly bound with each other, which confirmed with a large momentum transfer. Several different flavors of quarks were identified, unify different masses. Protons and neutrons consist only of the first two types. They are so-called as quarks, but it was necessary to introduce more types, three more up to today, in order to explain the numerous heavier short-lived mesons and baryons forming in nature. The different quarks types transform into each other only through weak interaction. Moreover, it was necessary to ascribe an internal degree of freedom to each quark. A traveled spin called color, which permits the quarks to exist in three distinct quantum states. So far, it has not been possible to ionize the hadrons that it liberated. liberated a quark from a hadron and observed it as a free particle. However, in high energy collision, jets of mesons have been observed with a large momentum exactly in the direction in which quarks should have been ejected. The process of mesonization of quarks is to some extent understood as the creation of a trail of quark anti-quark passing by the ejected quarks. The behavior of the quark has led to the conclusion that the forces holding them together are soft, that is weak, against a large momentum transfer action at small distances, and strong against a smaller momentum transfer action at a large distance. Indeed, the confinement of quarks possible of ionizing them indicates that the potential of the quarks binding force goes to as for large distances. Quantum chromodynamics (QCD) goes a long way towards explaining some of these features. It describes the strong interaction between the quarks by a non-abelian gauge field theory, a generalization of quantum electrodynamics in which the quarks are the source of gluon field and their charge is given by their tri-valued color degree of freedom. In the theory, the field comes charge, a feature that is characteristics of a non-abelian field theory. So far, the calculable results of the theory seem to agree with observations such as weakness of the interaction for large momentum transfers, but most important feature of the quarter interactions, the confinement of quarks, has not yet been derived from the theory. It has not been shown, however, that the theory definitely cannot account for it. Still, we are far from having a really reliable theory of quarks and quark interactions. The next decade may produce many new insights with this mysterious subnuclear realm of nature. Such new understanding is essential since QCD cannot tell us how many quark types exist and what their names are. It does not deal at all with the question. Indeed, the fact that these are more than the two types of quarks is already a deep riddle. The two quarks types with the lowest mass are the correspondence of neutrons and protons and prons. They make up nuclear matter as we know it under terrestrial and most stellar conditions. It is completely unknown why nature needs the heavier quarks that are the constituent of the strange and charmed head had rules which are all short-lived. Products of energetic collision that quickly decay with more ordinary particles such as nucleons, electrons, and neutrinos. Most probably the number of known quarks types will increase in the near future, since we expect more stable discoveries of quasi-stable structures that are quark-anti-quark combination. The initial discovery of three to four particles, a combination of charmed quark and antiparticle by Burton, Richter, and Samuel Tom in 1974 was one of these seminal experiments. It had already had one sequel indicating the existence of fifth quark. Many more will follow. The two near quarks discovered unknowingly in a period of 4 years should be enough. But physicists have also discovered a new heavy electron and particle of a mass near 2 GeV, which together with the and the mu are now forming a triad of charged leptons. The future will show whether it has its own neutrinos as do the others through electrons. The existence of at least 3 electrons differing only in their mass is a tantalizing problem. Here too we have no idea about the role and nature of these heavy electrons which decay by weak interactions with ordinary electrons after emitting suitable neutrinos, just as QCD does not tell us why these are several quark types. Quantum electrodynamics does not yet offer any explanations from the proliferation of electrons. Recently, a number of existing experiments and the theoretical developments took place in the field of weak electrons, weak interactions. They are connected with the construction of a unified theory of weak and ELN interactions, which I mentioned earlier. An attempt was made to unite these two phenomena by introducing a common field transmitting their interactions. The field has several components. One representing the photons as carriers of electromagnetism interactions, other representing the weak interaction. The unification solved not only some of the internal contradictions in the previous theory of weak interactions, it also required the existence of neutral qubits. The weak interaction process without transfer of charge. During 50 years of study of weak interactions, it was assumed that they are all connected with a charge transfer. A radioactive nucleus charges its charge when it delays the charge is transferred to the emitted electron. A heavy electron does not charge with a light one, but into a neutrino emitting another electron. Neutrino pair, electron-neutrino pair. The process without charge transfer escaped discovery, but a few years after their prediction by the unified field theory. Such processes were observed in neutrino-induced reactions, first at CERN and then elsewhere. Quite recently, in an interesting and difficult experiment at SLAC, the same neutral weak interaction was also observed between electrons and protons by making use of the violation of parity, which distinguishes it from the moment of stronger electromagnetic interaction. The theory predicted these and other weak interactions phenomena into astonishingly quantitative accuracy. The existence of carriers of weak interaction intermediate bosons have not yet been experimentally verified. If the theory is right, weak and EM phenomena will emerge at high energies in a predictable way, and a new type of particle, the Higgs particle, will appear. Time will show whether the theory are on the right tracking, but one thing is almost certainly true, and these high energies, that is mass energies of 100 GeV or higher, both the weak and the EM phenomena will exhibit properties very different for these to which we are accustomed. And there are two groups of elementary particles, that is the fermions, and to the subgroups, quarks and the leptons. Quarks are constituents of hadrons and do not exist as free entities. In the past, one new quark to B quark and one new L, that is the P particle, were added. We commend that we consider the proton and neutron to be made up of U and D quarks. Why does nature need the other quark types? This is the end of the notebook, so I'll stop here. Thanks.